Okay, the next problems we have, so I'm not going to do a bunch of those checkpoints, is density. So we need to be able to solve for density. And density is an intensive property. So what does that mean? That means it does not depend on the amount of mass present. Okay, so the opposite of intensive property would be extensive property. And an extensive property depends on the mass. And I think this is kind of interesting because what is the formula? So density, you could just make a heart, a broken heart, right? So the formula for density is mass over volume. So if you can see the M here and the volume there, okay? Now mass is extensive and so is volume. So if you pay so much money for an amount of something, you're going to get mad if you only get half the amount. Or what if you go to spend $1 on a 20-ounce soft drink and you only get 12 ounces, okay? So those are extensive properties. Density is a formula, it's a derived unit, and it is an intensive property. And you need to be able to work problems such as those. So let's pick problem number 1.3.4. Given the density of gold, AU, okay, you need to know your first 20 elements in the periodic table, so start working on those. Grams per centimeter cubed. Okay, so gram is a unit of mass, and you need to know that. Centimeters cubed, the cube means it's volume. So if you measure like a cylinder, a graduated cylinder in milliliters, you could also measure the height in centimeters, the width in centimeters, and then the height, width, and the depth in centimeters. And then when you take centimeters times centimeters times centimeters, that is centimeters cubed, and that is a volume. And so anytime you have a container that has a width, height, length, width, height, and length, it's 3 units, so it's cubed. All right, so there is our density. It says calculate the volume. So what do we want? We want the volume. So we want in centimeters cubed. And it has the mass. The mass is 5.98 grams. So what you want to do is you always write your formula out. Density equals mass over volume. And it wants you to solve for volume. So we have to isolate the variable here. So to isolate your variable, volume is in the bottom, and we want it to be volume equals. Okay, so we want our formula to be like that. So if it's in the bottom, mass over volume, to get rid of it, we have to multiply both sides by volume, and that's going to cancel out the volume here. Volume divided by volume cancels it out. So then you can rewrite V volume times density equals mass, but we want to isolate the volume because we're solving for volume. So how is volume connected to density? By multiplication. So now we've got to divide both sides by density, and then that will mark out the density because density divided by density. And then we can rewrite this. Volume equals mass divided by density. And now we have the formula like we wanted it to be, where we're solving for volume. We've isolated the variable, and then we can plug and chug. So now we say volume equals, what's the mass? The mass is 5.98 grams, and we divide by the density, and the density here is 19.3 grams over centimeters cubed, and the grams will cancel out, and centimeters cubed will then be on top. And so now I get my calculator out, and I do 5.98 divided by 19.3, and the answer is 0.3098 centimeters cubed. And how many significant figures? we go back to our problem and we see our measurement is 3 and 3. So our least number, the least number of 3 and 3 is 3 significant figs. So I need to report this to 3 significant figs. So there's 3, but notice that the 9, the 8 is after the 9, so I have to round up. So it's going to be 0.3. To round up the 9 makes it 10 centimeters cubed. And that is your volume. Now I'm going to look and see if I can find that answer. And I do. I see that answer is answer number letter D. And you can always check my work, check my math. I have done general chemistry, but I am an organic chemist, and therefore I don't use my calculator as often as other maybe analytical or physical chemists. So always check my math, and do not hesitate to send me an email and say, I think this was incorrect, so I can fix that. Okay, another checkpoint question is properties of matter. So we've talked about extensive, intensive a little bit. But we also need to understand if something's a physical change or a chemical change. In chemical change, we're going to be really working chemical changes when we talk about chemical reactions. We'll be writing chemical reactions and balancing chemical reactions and dealing with stoichiometry. So we'll be doing that, but that changes the substance. So this checkpoint problem is trying to ask you 1.41 and 1.42 is trying to discuss which ones are chemical changes versus physical change. So I will just say, like if you have water, so you can have oxygen represented as maybe, so oxygen is represented as red, and you can make the hydrogens represented as blue. That's water. And if you have water close together, these water molecules close together, so if we have 3 of them, maybe they're close together, and that would make them a solid. And then you do this arrow, reaction arrow, and you're saying, okay, afterwards, and you still have the water, okay, but it's further apart now. That would be a phase change. Okay, so this is a phase change. This might be a liquid because they're further apart. If you dissolve them with maybe sodium chloride, so if we do sodium chloride and we say we have sodium and we have chloride here, and when it's together, before you add it, it would not dissolve, sodium chloride. But then when you put it in water, this is an ionic bonding, we'll talk about that more, and you put it together and you break it apart in water, you're dissolving something, okay? So this would be dissolving when you put salt water, and this is a mixture. So what they're trying to ask you to do is kind of look for chemical reactions. So this would be a dissolving mixture. That would be a physical change. A chemical reaction is if you take something like water and then you make something different, and that would be like you make hydrogen plus oxygen. Okay, so now you have oxygen and you have water, and here you have, this is a different molecule, and this is water. And so those might be hard to see at first, but you're going to need to get used to looking at those, and you can go through those and see which ones are chemical reactions versus physical changes. So like I said, physical changes are like when you go from a solid to a liquid, and if you go to a gas, it would be even more spread out. All right, the other thing we need to deal with is significant figures and scientific notation. So the next problems I see on your checkpoint are 1.51. So let's look at significant figures. What does significant figures mean? Significant figures mean important figures. And they are important when you're recording how many grams are in a substance, or what you're eating. Those measurements tell people the certainty. So when do you have significant figures? You have significant figures in measurements. So you're going to be working in the lab and you have something here that might be 0 milliliters, 10 milliliters, 20 milliliters, 30 milliliters, 40 milliliters. Okay, so if you have something like this and you only have the markings for every 10, so if you only have the markings for every 10, then you would take your eyeball here and your meniscus, and you would see this here, and you could say, okay, I know it's between 3 and 4, and I can see that it goes past the 30, but you don't have the markings between there, so some of you might think it's maybe 32 milliliters. Some of you might think it's 33 milliliters. Some of you might think it's 35 milliliters. So this is the uncertain digit because we don't have any markings, and then we'd say this is two significant figures. Now, if you have a graduated cylinder that has more markings, and you come up here and this is, you can say 0, we'll just go between 30 and 40 here, and I'll make it big enough so we can see it. We have 1 markings for each one of these. 1, 2, 3, 4, 5, 6, 9, 10, and you fill it up here, and say you go to maybe here, okay? Okay, so then what do you have if you go here? Well, we all can say that it's definitely 30, and I don't know where this one would say. Let's say that's 30. 1, 2, 3, 4, 5. We can all say it's 35. Now, is it 35.0 milliliters or is it 35.1 milliliters? Is it 35.2 milliliters? We don't know. And we might all disagree on that last uncertain digit. So in this case, this measurement, we could take it out to 3 significant figures instead of 2 because of the markings. So when you get these written problems, whatever the number with the unit is, that's going to tell you how many significant figures you want to report. If you're actually taking the measurements in the laboratory, then you need to look at the markings on the instrument. So if you're in my laboratory, you can just ask me and I'll say, okay, this is the significant figures we go to. On the weigh balance, you always record whatever the numbers are on the weigh balance. So look at 1.51, what volume of water is in the graduated container to the proper significant figures. And you see that it's maybe, it goes up to 35 and then 31, 32. So you could probably see that 32 we could all agree on because we can see those lines. And then, but we don't know if it's between 2 and 3, so you might say 0.5 milliliters. You could say 32.2 milliliters. I'd look at the problems, and at that point, 31, 32, I would say A is your correct answer, or 32.5. 32.5. I would say it's 32.2. And so that's how I look at that. All right, so let's look at what about in significant figures when you're, so that's measurement. What about significant figures when you're doing addition and subtraction? So let's look at 1.52. It wants the sum 3.115 plus 0.2281 plus 712.5 plus 45. Now when I'm doing these, I like to line up the decimal. So I will rewrite them. And I will line up the decimal 2281. And then here we have 712, and we have 45. And then you can add all of these up. 1, 8, 9, 10, 11, 12, 13, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 10, 4, 5, 6, 7. Now, in addition, it's the least number of significant figures past the decimal. So you can say this one has 3, this one has 4, this one has 1, and this one has 0. And so then we have to report, we'll have to round that up from the 8. So the 8 will round this 0 to a 1, so 761. And so E should be your answer. Now if this is multiplication and division, like you have in problem 1.54, 6.266 minus 6.261, and then you divide that by 522.0, well, you do your please excuse my dear Aunt Sally. These are your orders of operations. P is for parentheses, E is for exponents, M is for multiplication, D is for division, A is for addition, and S is for subtraction. So that's your order of operation. So we're going to do parentheses first. So on my calculator, I'm going to do 6.266 minus 6.261. And I'm going to write in there 0.005. And then we're going to divide that by 522.0. And we get 0.0000, 1, 2, 3, 4, 5, 9579. And so now we got to look at our significant figures. This is subtraction, and so that has 3 significant figures past the decimal. Okay, so that was really 0.00500. Now how do I know that? These are insignificant. The zeros to the left. So really when you're trying to figure out whether to count, you're counting zeros. Okay, think about this. We're looking at insignificant, okay? Insignificant means not important. We don't count it, we don't care. Remember that song, to the left, everything young to the left? She's breaking up, right? She's breaking, is that Beyonce? She's breaking up. It's insignificant, so putting everything to the left. So zeros to the left are insignificant. They're not important. So see these zeros to the left of the 5? Not important. They're insignificant. So here we have 3 significant figures, so 5 is one of them. And then we got to add 2 zeros. So that's 3 significant figures. Now, that's for subtraction. But the rules for division are overall significant figures. Okay, so here we have 3, but here we have 4. So what's lower? 3. So that means I got to report this to 3 significant figures. So I do the whole math on my calculator, and then I realize that these are the 3. And I'm going to have to round up because of the 9. So it's going to be 958, and we're going to put this in significant or scientific notation. 1, 2, 3, 4, 5, 6. So it's going to be 9.58 times 10 to the negative 6. 1, 2, 3, 4, 5, 6. That's going to be your answer. And let's just look at this. Why is it negative? Well, look at your overall number. That's how I know negatives and positive. Is this overall number less than or greater than 1? The overall number is less than 1. That means the exponent better be negative. It's small. If this overall number had been greater than 1, your exponent should have been positive. Okay, so do we have a 9.58 times 10 to the negative 6? C, yes, we have C as an option. And you can check these answers. I probably should check them too. Um, all right, so the other one, deciding between precision and accuracy. Okay, so one of our goals is to look at the difference between precision and accuracy. So let's say I go to the doctor's office and they weigh me as 121.5 pounds. Okay, now I go and sit on my weigh scale and it says I weigh 115.5 pounds, and then I get on there 3 times. I weigh 116.0 pounds, and then I get on there and I weigh 115.5 pounds. Now I'm really tickled to death. I like this weight better, right? Is it precise? Yeah, I think it's pretty precise. I mean, it wasn't like one time I got on there and I weighed 115, and the next time I got on there I weighed 120, and the next time I got on there I weighed 122. So it's precise. The numbers are close together. But is it accurate? No, it's not accurate. Okay. So accurate would be closer to the 121 because the doctor's office is supposedly calibrated and accurate. Okay, so if you look at your problem in 1.53, and it's asking which of the data has the best accuracy and which has the best precision, respectively. So that means you got to answer your first question with accuracy, comma, precision. That's what respectively means. So which one's accurate? Well, what's on that line? Do you see the green? So the green is right on the line. So I would say green is accurate. Okay. And which one's more precise? Which numbers are closer together? Do you see that you have this purple one over here that's really close together? Those numbers are tighter. So the purple would be your more precise. So you will see questions like that. All right, so your next questions are in your section 1.6, and we're doing unit conversions. So let's try a few of those. Okay, we've already worked a density problem. Let's convert 43.1 centimeters to liters. So this is 1.6.2. Now you do need to know your unit conversions. And so 1 centimeter cubed equals 1 milliliter. Okay, so some of them you just need to memorize, and that is one of those that you need to memorize. Let's see if there's usually in your chapter, there is a list of units that you need to memorize. And so I think it's in your book, page 10. They have some, not all the ones you need to memorize. I'll have to help you out to find those. But apparently you have your metrics SI units. You do have to know those, and that will help you. Okay. The other one, 1 milliliter equals 1 centimeter cubed. You see that on page 13. I do expect you to memorize that and know that, okay, because it's how you can go from centimeters to milliliters to liters. All right, so here is our problem, and we're going to do dimensional analysis. So this is your known. This is your given. You have a number with a unit, and that's where you always start. Then you put that over 1, 43.1 centimeters cubed, and you put that over 1. And then you can call these railroad tracks or whatever. But you always put what you don't want on bottom. Okay, so you want centimeter cubed on bottom because we want to go away with that, and we want to go to liters. So the thing is, though, we can't just go from centimeters to liters. We did in our toolbox, we can call this our toolbox, we do have conversions that we memorize. We can go centimeters to milliliters, and then, but we need to be able to go to milliliters to liters. So here we have to memorize that milli means 1,000, and the base unit is liters. So milliliter is smaller. than liter. And so I always remember that the big number always goes with the smaller unit. Okay, so think about it. So what's bigger? And the letters are always your unit. Are pennies or a dollar bigger? Okay, so we all agree that a dollar is bigger than pennies, right? And how many pennies are there in a dollar? 100 pennies in $1. And this is a conversion factor and they equal each other. But you see how the bigger number goes with the smaller unit because it makes it up. Okay, so you have to memorize the metric center, metric units. And so M is milli and it means 1,000. Okay, and it's smaller than liter. So here we can go from, and let's just focus just on centimeter. We can go from centimeter to meter. Okay, let's not focus on the 3. Well, what's centimeter to meter? Centimeter equals meter. Well, centa means what? Means 100. So there's 100, and centa is smaller than meter. So 100 centimeters into a meter. But we're not going to put that on there yet. We don't want meter, do we? So we're going to put meter on bottom. And what do we want? Oh, we don't have to do that because we're not doing, we have this conversion. Hallelujah. All right. Makes things a little easier. So we can go straight to centimeters to milliliter. Okay. So, and we know that we have 1 and 1. Okay, so this one's going to be easy. And so the centimeters cubed and the centimeters cubed cancel out. So 43.1 times 1 is 43.1 milliliter. And let's see if you get that option. Oh, it wants liters. Okay, so then we do 43.1 milliliters. We don't want milliliters, so we're going to put milliliters on bottom, and we go to liters. And so now we put 1,000 with the milliliters and 1 with the liters. Now, if it's on bottom, you divide. So now I'm going to get my calculator out and go 43.1 divided by 1,000. That is 0.0431 liters. And I look and I see that that answer is C. Another question, 1.6.4. How many cubic centimeters are in a cubic meter? This is an important one, okay? So, well, don't use the cube. What's a centimeter equals meter? Well, what number? 100 centimeters in 1 meter. Will we agree? So then if we want to cube it, centimeters cubed, we also have to cube the number. So we cube that. And we cube the 1. And we cube the meter. And so what's 1 times 1 times 1? That's 1 meter cubed. Now I'm going to actually get my calculator. 100 times 100 times 100. That is 1, 2, oh no. Go back to normal here. Okay, that is 100 times 100 times 100. Did you get 1, 2, 3, 4, 5, 6 zeros? Centimeters cubed. So that is the answer. There is, if we convert that to scientific notation, that's a big number. 1, 2, 3, 4, 5, 6. 1 times 10 to the 6th. And is that a big number, greater than 1? Yes, so it has a positive exponent, 1 times 10 to the 6th. So E is your answer. Let's see if we can find an additional problem on our list that has some conversion unit factors. So I am looking on page 33, and let's work out a couple of these. So we're going to do 2 of these. Let's do 1.56D because these are a little bit more challenging. All right, so it says 10.6 kilograms per meter cubed, 2 grams per centimeter cubed. Okay, so this is our given because it has a number with a unit, 10.6 kilograms. There's not a number with the meter, so we're going to put this all over 1 meter cubed. Okay, so that division here, right here, is that right there. And then if you don't have a number there, you assume that it's 1. So there's no number there, so we assume it's 1. Okay, this is our starting. Now we want to go to grams. So we want kilograms to gram, and we want meter cubed to centimeter cubed. And so now we have to pull in our what we call our toolbox, okay, our thinking. Do we know any conversions to go from kilograms to gram? Yeah, so 1 kilogram equals 1,000 gram. Because kilo is big, babe. Okay, that's a big number, and it means 1,000. So 1 goes with kilogram, and 1,000 is the smaller, and it goes with gram. Okay, so now we can, if we have kilogram on top, we need kilogram on bottom because we want it to go away. And we know we can go from kilogram to gram. We'll put our numbers in a little bit later here. But we will hold on to this conversion factor. Now, we also need to focus on going from meters to centimeters. Don't worry about the cube right now. We're going to go meters to centimeters. Do we have a conversion factor to go meters to centimeters? So we know that centi means 100 and the base unit is meters. So 100 into 1. Okay, now if we want to cube it, we got to do 1 cubed meters cubed equals 100 cubed centimeters cubed. And now, so 1 times 1 times 1 is 1 meters cubed, and 100 times 100 times 100 is 6 zeros, right? Cube. So here is our other, let me put that back. I'm trying to highlight it. All right. This is our other conversion factor. So now, this takes care of kilogram. So we're at gram. So we're good there. But now we got to get rid of meters cubed. And meters cubed is on bottom, so we're going to put meters cubed on top. All right. And we're going to go from meters cubed to centimeters cubed because we have this here. And we can go from centimeters to meters. And it doesn't matter top or bottom. This over here decides what's going to go on top and bottom. Okay, so this is going to give us grams on top, and it's going to give us centimeters on bottom because these units cancel out. So we know we have it set up correctly. Now we have to put the correct numbers in, so you don't want to mess this up. So 1 goes with kilogram and 1,000 goes with gram. And then we come down here and 1 goes with meter cubed, and 1, 2, 3, 4, 5, 6 goes with centimeters cubed. Now, I just go from left to right, and I do 10.6, and then that's divided by 1, so don't worry about that. So then I take times 1,000, and I hit equal, because I need to do that on my calculator. I don't worry about the 1. I don't multiply it by 1. Now I'm going to take that number and divide by 1, 2, 3, 4, 5, 6, 1 and 6 zeros, and I get 0.0106 grams per centimeter cubed. And then I'm going to look at my significant figures. It's always the given. It's the starting one. 3 significant figures. This is just multiplication and division. So there's my 3. And that's my answer. If you want to put that in scientific notation, you would do 1.06 times 10. And you move the decimal 1 2 places. And it would be a -2 grams per centimeters cubed. And you know it's negative because this number is less than 1. So if it's less than 1, it needs to have a negative exponent. All right, I guess we'll just stop there. And hopefully this has helped you start understanding how to solve problems in science.